Good morning. We'll give everyone a minute or two to log on. Hope everyone is having a great week so far. Happy to have you join us today. Just another minute here so we get some critical mass. Thanks for joining. Good morning, everyone. Right, I'm gonna go ahead and get started and let folks join, since I know that there's quite a bit of content we need to get through in an hour. Good morning, John. My name is Bryn Oakleaf. I'm the EN program manager with Efficiency Vermont, so the Efficiency Excellence Network, if you aren't already familiar with it. I'll be facilitating today's webinar with Chris Smith from Zehnder. Thank you for joining us today. And if you're not used to the controls at the bottom of your screen, you should see a chat feature, you should see a raise hand option. Certainly use those throughout the session. To ask your questions, no need to wait till the end. We'll pause throughout, since it can be quite a bit to get to at the very end. This is a 1-hour webinar. We will be probably cutting it tight, but hopefully we will end on time. Certainly feel free to stay a little longer if you have additional questions. And I know Chris has his contact information as well. But we look forward to having Chris Smith from Zehnder join us and give us an excellent presentation today. Thank you so much.
Thanks, Bryn. Hi, everybody, and thanks for jumping in this morning. As Bryn said, there's a lot of content. I'm going to bring up the slide deck and we'll get started. And I'll introduce myself as soon as we do. Okay. I'm with Zehnder America. Zehnder is a Swiss-based company that is involved in climate control and mostly focused on clean air and healthy environments. So Zehnder America is the North American branch of the Zehnder Group, and we focus entirely on energy recovery ventilation. So we've got a lot of information to share if you want it, but we've put together this presentation. This is pending AIA approval right now for AIA credits, but hopefully that'll come through and we'll be able to offer that to you. I'm the business development manager for Zehnder America. My background for years was in design and residential construction. I got involved in the healthy home movement for a bit because of needs that clients of mine had. And that's what led me to focus on indoor air quality and eventually connected me with Zehnder. And now I'm pretty pumped about seeing North America's indoor air climate improved as we learn to focus more and more on the best practices in residential ventilation. So that'll be the thrust of what I share with you today. This is an introductory presentation, so there's really nothing, you know, I'm assuming most of you, if you've chosen to log on here, you've already got the requisite, you know, familiarity with building and et cetera. This is energy recovery ventilation can be a dry topic. And I always imagine that most people, when I'm 10 minutes into it, are snoozing. Here's what's not dry, and I want to just focus on some features that I think will help us realize why this is important. These are the things that matter to people. People want a healthy living and working environment, a place where they can feel good, feel their best, and feel like they're doing well for their families. People want to be able to function daily with an alert, productive mindset. That's important. People want restful, recuperative sleep. So, you know, waking up in the morning feeling like you've actually slept 8 hours or whatever you've managed to get. Thermal comfort is important to people. And just basically smelling like you have fresh air, an odor-free breathing zone is important to people. Obviously, we want to reduce our carbon footprint as best we can. And we want to, at the same time, lower our utility costs. And all of this, if it's done well together, can actually result in a more durable home. And of course, anybody who owns a home wants that as well. Even for those who rent, they're best off if they're in a durable building. So these are the features that, that energy recovery ventilation can contribute to if it's done well. And so we want to focus on best practices so we can arrive at those kind of outcomes. Today, our learning objectives will be: number one, to associate ventilation with air quality characteristics. Number two, distinguish between potential methods of ventilation. Then number three, recognize and mitigate the energy penalty of ventilation. And lastly, number four, we'll briefly identify some highly effective energy recovery ventilation solutions. So which we'd be looking for when we want to do best practices. So number one, let's associate ventilation with air quality characteristics. We know that today's homes are constructed with a whole series of barriers. We have weather barriers, thermal barriers, and now we're focusing more and more on air barriers. And when we do these things well, it's really effective at improving comfort and building durability. It's really good at saving heating and cooling costs and reducing energy consumption. So those things are all great, and that's why we've been getting better at these techniques. But when we effectively employ this combination of barriers, we also restrict natural airflow, and we trap pollutants, air pollutants inside the building. A house, I don't know if you think about it this way, probably not, but a house is basically a gas state aquarium. It's an enclosed volume of fluid, not water, but air, but nonetheless, it's an enclosed volume of fluid, and that fluid has different characteristics or different quality of composition than the volume outside the enclosed space. So really, we're living in fish bowls. Under normal conditions, most indoor air is more polluted than the outdoor air. That's again because of our very effective system of barriers. We've trapped all the things inside our homes that come in or that start inside. And the EPA says that indoor air can be as much as 5 times more polluted than outdoor air. Some typical indoor air quality contaminants are things that are actually pretty normal. It's not exotic stuff. It's stuff that's around us all the time. As we said, the indoor volume of air is basically a fluid. It's a solution. The primary gases in our atmosphere are nitrogen and oxygen. There are others in lower concentrations, but those are the primaries, and they could be thought of as the solvent. But we have other things dissolved in this fluid solution. PM 2.5, microorganisms, moisture droplets, things like that form aerosols within the air fluid. And then we get VOCs and CO2 and maybe some odors that are gaseous things that enter into that solution in lower concentrations. But these things change the quality of the fluid that we're walking and sleeping and breathing. So what does ventilation do? Ventilation is basically air exchange. When we talk about buildings ventilating, we're talking about outdoor air being exchanged with indoor air. Outdoor air is supplied to the building in some way. Indoor air is exhausted from the building in some way. And as that happens, that indoor fluid, the concentration of contaminants inside that indoor fluid is diluted. And that's good. That's what we want to do. And that's why we ventilate. The higher the flow rate of ventilation, the faster the concentration of pollutants is reduced. So let's talk about ventilation and air change. We can establish an air change rate. And if we do that, we can match it to the building size. And over the course of time, the indoor air pollution will be replaced with cleaner outdoor air and will reduce the concentration of the pollutants. If the ventilation rate is pretty constant, then we'll reach a near steady state of indoor air quality contamination that's acceptable. So the proper ventilation rate, the rate we want of exchanging outdoor air with indoor air, is a rate that sort of matches the rate of the generation of the indoor air quality contaminants. And that's how we get to our steady state. And there are, some suggestions in the industry for what those rates are. Just to illustrate for a bit, this is a chart showing 1 week's time in a new construction house. This is back in 2016. And what was measured was VOCs. VOCs are volatile organic compounds. They're basically things that are off-gassed. And in this case, it's pretty much from building materials and finishes, because this was a new constructed home. People weren't living in it yet, but it had been commissioned and the ventilation system was operating. And what we're basically looking at the beginning of the week, the vertical gray lines, the faint gray lines are each demarking a day. At the beginning of the week, we see 2 days where we're operating at a fairly consistent ventilation rate. And that ventilation rate was 0.6 air changes per hour. So, basically 2/3 of the entire building volume air was being exchanged every hour. They did an experiment and shut off the ventilation system for about 2 days. And over the course of that 2 days, you can see the VOC concentration spiking up north of 1,700 parts per billion. And that's a really rapid and marked spike. They turned the ventilation system back on, let's see, about day 4, and turned it on at a slower rate. So now it was only getting about 1/3 of the air volume being exchanged per day. And we can see the rate there. Somebody walked in the door at some point about day 5, and you see a drop as the doors were open and people were moving around, and then they went out. And then later on in day 5, they ramped the ventilation rate back up to that 2/3 air changes per hour, and we see the VOC rate steady or level out again, more or less. So just an example of what happens, how air quality is impacted by ventilation and the ventilation rate. Another slide, this is a little bit dizzying, but basically I'll just simplify it for you. We're looking at CO2 levels plotted out in 4 different apartments. And in those 4 apartments, we're looking at either 2 or 3 different rooms. The CO2 levels are color coded. So the green is less than 800 parts per million. That's considered, not bad, pretty decent air quality. 1,000 parts per million of CO2 is sort of the recommended limit to be living with all the time. Above that, and you begin to experience degraded cognitive function. Could be pretty slight at first, just a little fuzziness or a little distractedness. But as you climb up, you actually they've tested and they can see people have harder times making good decisions or processing more complex levels of information. So we want to stay below 1,000 parts per million. The yellow in these charts is a range between 800 and 1,000 parts per million. And then the red is above 1,000 parts per million. So what we're looking at in these 4 different apartments is the 2 top apartments, basically just didn't have ventilation systems. They just had windows that the occupants could open or close. And we're looking from left to right at a whole year's worth of data in these carpet plots. So throughout the course of a year, you can see on the one on the right, for the top right apartment, for example, there's a lot of red in the middle of that year. That's the winter time. And of course, in the wintertime, you're less likely to open the windows. And so we saw high CO2 levels. The bottom two apartments actually had really excellent ventilation systems that were running continuously at a fixed rate. And so we see mostly excellent air quality, sometimes sort of moderate air quality, but very, very little time spent in that what's considered overdose. So, and CO2 is interesting. We'll couple of times today we'll talk about CO2. CO2 is the easiest sort of contaminant to measure. It's what's given off as we breathe, and so it's a really good indication of occupancy. And occupancy is a pretty good indication of air quality issues. And what's been found is that if you can measure CO2 and see where its levels are, you have a pretty good representation of what the other sorts of indoor air quality contaminants are like. So that's why this is interesting. Anyway, bottom line is that a good consistent ventilation rate improves indoor air quality in a measurable way. So we've sort of associated ventilation rates with indoor air quality. Learning objective number 2 is we'll distinguish between potential methods of ventilation. So we know we want to ventilate. We know we want to exchange indoor air with outdoor air. How can we do that? And there are 2 basic ways of doing that. One is sort of natural, and the other is mechanical. Those are really generic breakdowns. Natural ventilation could be done with windows or maybe some vents, or more likely it's done just by infiltration. Infiltration basically amounts to leaky walls and leaky roofs. Mechanical ventilation is ventilation that's controlled with fans, a fan or fans. Could be exhaust ventilation, could be supply ventilation, or it could be a combination, exhaust and supply done in a balanced way, balanced ventilation. So let's look at natural ventilation. Air exchange is basically driven by naturally occurring pressure differences between the outside and the inside of the building. So these are either wind pressure or stack effect. Wind pressure is pretty obvious. The wind blows on one side of the building, and if there's an opening or a crack or a leak, the air will be forced into that side of the building. The building would be pressurized, and air will escape as it can find a way out the other side of the building. Stack effect is a little less intuitive, but maybe still somewhat intuitive. Basically, warm air rises. So in a building, if the air in a building is being heated, let's say whether it's solar gain through the windows, or there's a furnace operating inside the building, but the air inside the building is being warmed, the warmer air will rise to the upper levels of the building, and the cooler air will be located in the lower levels of the building. There are usually leaks or a chimney or a vent or an open window in the upper level of the building where the warmer air will escape. This will depressurize the building, and by depressurizing the building, it creates a vacuum, so to speak, in the lower levels of the building. And so cooler outdoor air is pulled in through the lower levels of the building as the building operates like a stack or a chimney. Infiltration and exfiltration are pretty common in almost every building. Some buildings are more or less airtight, and so you might have more or less infiltration. But basically, these leaks occur around windows, doors, around pipes or at seams or openings. Oftentimes it's openings in the ceiling plane or the roof where vents or lights are mounted. And the seams between building components, whether it's panels or different different building assemblies. These are all places where leaks occur in our buildings. And wind pressure and or stack effect will exploit these leaks. So when we have this happening, when we have infiltration happening, we have air exchange. So in a sense, we have ventilation, but it's really uncontrolled. It's difficult to quantify. It's difficult to count on. And the fresh air, quote unquote fresh, the outdoor air that's being brought in is often polluted by the damp or dirty pathways that it's taking into the buildings. It's taking, the dirty, leaky, basement cracks or places like that into the building. So it's not the best method of reliable, healthy ventilation. Natural window ventilation can be, healthy and you can control it a little better. And it can be economical at times, but really only when the weather is favorable. We don't want to do window ventilation in the frigid winter or in the blazing summer. And even if we did, it's difficult to manage. Well, how much ventilation are you getting? This cartoon shows this guy trying to sort through the math of window ventilation, and it's a little bit futile. So typically we're used to approaching things in a more modern way, a more predictable way, and we use mechanical ventilation. The features or dynamics to consider with mechanical ventilation basically are, the airflow, the amount of airflow, the positive air pressure or negative air pressure that we're developing using fans, and then what impact air infiltration has based on that strategy. So we'll look at supply, exhaust, and then balanced ventilation. Supply ventilation is basically where a fan is pulling outdoor air in and blowing it into the house. And so what happens as we blow outdoor air into the house is we're bringing in some fresh outdoor air. We're positively pressurizing the house. And then because the house is under positive pressure, indoor air is being forced out of the house through, again, whether it's open windows, vent of some sort, most likely some sort of exfiltration through cracks and leaks. So that's supply ventilation. Exhaust ventilation is very similar, except instead of forcing outdoor air into the building, you're forcing the indoor air out of the building. And so instead of positively pressurizing the house, now you're negatively pressurizing the house. When you do that, you're not driving exfiltration, but instead you're creating a vacuum and you're driving infiltration. Again, if you're using an exhaust fan and negatively pressurizing the house, that vacuum could pull air in, outdoor air in through open windows or vents. But again, most likely it's pulling it in most of the year through cracks in the building envelope. And so you're experiencing infiltration. Now, with supply ventilation and exhaust ventilation, you usually have a pretty easy installation, one or more fans, and, easy duct systems, usually pretty easy. And you don't have to think about much more than that. But again, you're mostly relying on infiltration or exfiltration. With supply ventilation, you can control where you get your supply air. But with exhaust ventilation, your supply air, again, is still coming through the sort of nasty cracks of the building. So you're not controlling air quality all that well. And you're basically losing energy. Balanced ventilation uses a combination of exhaust and supply fans. And so now you're not necessarily relying on infiltration or exfiltration at all, but you can control the negative and positive pressure differential using your fans. And so you just get better quality control over your indoor air ventilation using a balanced mechanical ventilation system. This is good for the building. Supply and exhaust ventilation, either with that infiltration or exfiltration, are forcing air at different times of the year, relatively hot, humid air through the building assembly. And at different times of the year, that could result in condensation inside the building assembly. When you use the balanced ventilation system, you eliminate that risk. But let's talk about the energy penalty. Learning objective number 3 is recognizing and mitigating the energy penalty of ventilation. So, you know, we've sort of recognized that window ventilation, while it's easy and effective as a ventilation strategy, it's not really practical year-round in most climates. The outdoor air is often either too hot, humid, or cold to be comfortable. And so if we open the if we open the windows in order to get the fresh air, then we're going to continue to run the heat or the air conditioning in order to get the proper level of comfort inside the house. And that's kind of foolish to open the window just to run our conditioning systems more. We probably wouldn't do that. Common sense would say you don't leave the windows open all winter long. But unfortunately, in some cases, mechanical ventilation is really no different, because when we're using supply and exhaust fans to drive our ventilation, that infiltration and exfiltration is really, it's the same volume of air coming into the building. And because we're changing outdoor air with indoor air, we're changing the temperature of the air in the building. The set point on our thermostat will be triggered, and our heating or cooling conditioning systems will be running more to deal with that mechanical ventilation. So this additional heating or cooling energy can be estimated with a pretty basic calculation. And the result of that calculation is what you can call the energy penalty of ventilation. So a simple way of estimating that energy penalty is by using this calculation. You can arrive at your BTUs per hour, your energy penalty, by multiplying a basic multiplier times the ventilation rate in CFM times the difference in temperature. And so if we, in this case, we'll use 1.08 as the multiplier. This is basically relating to air's ability to carry heat at a certain density. We'll use CFM as our ventilation rate, and the difference in temperature, we'll use Fahrenheit, and this is the difference in temperature between outdoor air and indoor air. And we can arrive at our BTUs per hour. So let's say we're ventilating with an exhaust fan only, just as an example, of 100 CFM. So that's our rate. 100 cubic feet per minute of outdoor air is being sucked into the house through infiltration. It's unconditioned. Let's just say that the outdoor air is 22 degrees. It's a brisk winter day. And the indoor set point is a common 72 degrees, comfortable temperature. So our equation would be 1.08 times 100 CFM times 50 degrees Fahrenheit. And we'd get an answer of 5,400 BTUs per hour. So 5,400 BTUs per hour, or 1.6 kilowatts, would be the energy that's being wasted, or the energy penalty associated with using a bathroom fan to achieve 100 CFM ventilation rate. And by the way, 100 CFM ventilation rate is not an unusual ventilation rate for a residential building. And 5,400 BTUs per hour, or 1.6 kilowatts, that's big enough to impact the size of a heating system required to condition the house. And this could, depending on the climate you're in, if you're in a Vermont climate, for instance, this could account for over 100 gallons of heating oil every year. So it's significant. Look at a hot climate example. Let's use a similar scenario, but let's switch the outdoor temp to 92 instead of 22. So now our delta T is 20 degrees. If we run our same calculation, we're going to arrive at 2,160 BTUs per hour, or a little more than 0.6 kilowatts. So this may or may not quite change the size of the cooling system, but it's definitely going to change how much that cooling system operates. And it can account for hundreds of dollars in extra electricity to run the AC. And that's just to talk about the thermal side. If we talk about humidity, there's even more impact. In many climates or many portions of North America, there's a lot of humidity during much or most of the year. And in some cases, 100 CFM of ventilation could introduce almost 200 pints per day of moisture into the building. And so, you could be looking at another 1.5 kilowatts of electricity just to run the dehumidifier to deal with that ventilation, if all you're doing is some sort of exhaust-only ventilation. So balanced ventilation with heat recovery is a solution. We want good indoor air quality, so we want to ventilate. We recognize that ventilation can cost a lot of money. Besides just the fan energy, it costs in conditioning energy. So we want to be able to recover that ventilation, and we can do that with energy recovery ventilation. An energy recovery ventilation system is basically a balanced ventilation system that includes both the supply and exhaust fan. That's the starting point. We've already acknowledged that, but we want to find some way of achieving the ventilation or the energy recovery. What we're going to do is find some way of efficiently transferring energy between the supply air and the exhaust air. So we're pulling air into the building and we're exhausting air out of the building. How do we change energy between those air streams? In the winter, we've got warm indoor air. We've spent money to condition that. So we want to be able to extract energy from our indoor air and introduce it to the incoming outdoor air. In the summer, we want to do the opposite. We've spent money to cool the indoor, so the energy is all in the outdoors. We want to transfer that energy to our exhaust air and send the energy back outdoors and maintain our cool environment indoors. So there are different methods of doing this. Just to real briefly, we'll look at a couple of methods that are not very common in they're commonly used, but not common in residential settings in North America, at least not in 1 and 2 family. You might see these more in multifamily situations, but one is a rotary heat exchanger or an enthalpy wheel. You commonly hear of an enthalpy wheel or a heat exchange wheel. And this basically has the supply air duct and the extract air duct located right next to each other, where you have a wheel that is located in between those two ducts. And as the wheel spins, the wheel is made up of a coil of sort of corrugated material. And so as the wheel spins through whichever of those air streams is the warmer, depending on the season, it will collect the energy from that airstream. It will rotate around, and then as it goes into the other airstream or the other plenum, that airstream will collect the energy and deliver it. So if it's wintertime, it'll collect the energy from the indoor and then spin around and deliver it to the outdoor air. So as the outdoor air is delivered to the building, it is coming in warm. Excuse me. A heat pump uses a different technology, but again, it's accomplishing the same goal. We want to move energy from the warmer airstream to the cooler airstream so that we can maintain our indoor climate. The heat pump uses heat pump technology, an evaporation cycle, refrigerant loop. So we're pretty familiar with heat pumps. It's what our refrigerators operate on. It's what our air conditionings operate on. And if you have a A mini split heating cooling system, it's what that system operates on. You're basically just using an air-to-air heat exchanger or air-to-air source heat pump to collect air from the warmer portion and deliver it to the cooler portion. And that can be reversed depending on the season. Just mention again, in both of these, you have a supply fan and exhaust fan in some way of moving or transferring the heat between the two airstreams. A fixed plate heat exchanger is the much more common type device that's used in North American 1 and 2 family energy recovery solutions. So we're going to focus on fixed plate heat exchangers for the rest of the presentation. A fixed plate heat exchanger uses no moving parts besides the fans. So you have a supply fan and exhaust fan as you do with the others, but other than that, you just have this system of fixed plates. These are very thin plates. They have ridges stacked together, forming a wafer-like structure. This creates hundreds or even thousands of adjacent channels. And these tiny supply and exhaust air channels are located adjacent to each other. Exhaust and supply air can pass by each other without ever mixing. As air passes through the heat exchanger, the energy in the warmer airstream moves across the thin plates, does that via conduction, and it's picked up by the cooler airstream. And depending on the size and shape of the heat exchanger and the speed of the air moving through it, you can get really, really high energy recovery. The simplicity of this heat exchanger can be provided in a pretty compact appliance. And this single appliance can include an insulated cabinet, the heat exchanger itself, the supply and exhaust fans can be located inside the cabinet, along with the filters and the controls, and you can have your duct connections. It becomes a pretty compact device for everything it accomplishes. Let's talk briefly about HRVs and ERVs. In general, we're talking about energy recovery ventilation, but more specifically, we can talk about a heat recovery ventilator, which transfers heat only. Sometimes this is referred to as sensible recovery, or we can talk about an ERV. An ERV is more broadly talking about energy recovery, and it transfers both heat and humidity. So, if we talk about heat in the traditional sense, we're talking about sensible recovery. Humidity, we're talking about latent recovery. Latent and sensible heat are both parts of enthalpy. In these pictures, we're looking at some examples of two different types of plates in these fixed plate recovery devices. The top is more rigid plates in a heat recovery ventilator. The bottom shows a more membrane-based plate. It's a vapor permeable membrane, so that the heat the humidity as well as the heat can transfer through the membrane. The differences in structure accomplish different things. They also require different manufacturing processes, and they result in slightly different recovery profiles. If we look at an HRV or heat recovery ventilator in winter, we can see that on the right side of this diagram would be your indoors. On the left side of the diagram is your outdoors. So this is winter, so outdoors is cold, indoors is warm. The extract air starts in the upper right, and it flows through the heat exchanger and is exhausted out of the house on the lower left. The outdoor air starts in the upper left, is cold air outside, flows into the heat exchanger, crosses through, and is delivered to the house on the lower right side of the diagram as supply air. So we're looking for the HRV to help manage energy transfer between these two airstreams, and that's exactly what it does. The heat from inside the building is transferred from the extract air through the heat recovery core into the supply air and then re-delivered back to the house. However, the air itself is kept distinct so that the exhaust air is delivered outside and the fresh outdoor air is delivered inside. The result is a comfortable indoor air supply temperature. Notice that the humidity in winter, your indoor air is going to be more humid than the outdoor air is typically. Notice that with an HRV, there's no humidity transfer. And so the exhaust air, while it gives up its heat, it maintains the moisture. And so the moisture in the extract air is exhausted to the outside. Now, if we look at that HRV functioning in summer, we have a slightly different scenario. The physics of it are the same, but the results are going to change. Same thing, left-hand side of the diagram is outdoors. The right-hand side of the diagram is indoors. We have fresh outdoor air, but very hot and humid in the upper left. That's coming into the heat exchanger. We want the heat exchanger to effectively take that heat and deliver it back outside. And so it's able to do that in a heat recovery ventilator. And so the exhaust air grabs the heat and pulls it back outside. We would like to not bring in all that outdoor humidity. However, an HRV has no humidity transferability. And so the humidity from outdoors is brought inside with the fresh air. Now, if we look at an ERV adds the ability to transfer humidity as well as heat. So now let's look at the ERV in winter. Again, in winter, our indoors is typically more humid than our outdoors. The ERV is able to transfer heat between the air streams, but it's also able to take some of the indoor humidity and retain some of that for comfort. Now, the ventilation rate will be sufficient if designed properly, that we won't retain too much humidity in the winter. You notice that the exhaust air still is carrying some of the humidity outdoors. But with an ERV, we're able to retain some moisture indoors along with the fresh air delivery. And so we maintain a healthier indoor environment that is able to stay relatively comfortable. In the summertime, in a hot, humid scenario, the ERV is also valuable because it's able to reject a lot of that outdoor humidity as well as the heat. Basically, the cooler, drier indoor air is going to pull heat and humidity from the outdoor air inside the heat exchanger, and it's going to deliver, as it's exhausted outside of the house, deliver more of that heat and humidity to the outside of the house. The fresh air that comes into the house will be close to room temperature and will have given up a lot of the outdoor humidity. So it comes in fairly comfortable. So which should we look for in our designs? Should we look for an HRV or an ERV? Well, in most cases, an ERV is more desirable than an HRV because of the ERV's ability to help manage moisture levels in the supply air. I say help because we need to remember that an ERV doesn't have a humidity set point. It's not a humidifier or a dehumidifier, but it's a passive device that can very effectively help mitigate the need to run other equipment as much to control the humidity levels. So an ERV is usually the most desirable choice. Now, what are the exceptions? The exceptions are in specific climates, maybe an HRV is better. Let me debunk the north versus south conventional wisdom that's floated around for decades. It's not as simple as northern cold climates want HRVs and southern hot climates want ERVs. We've explained why a cold climate can benefit from an ERV. So really, it's more that specifically climate zone 4C, which is Pacific Northwest marine climate, that's the climate where an HRV is usually preferable over an ERV. in almost every other scenario, an ERV is preferable. Other exceptions might be really high density occupancy. If you've got a dog kennel or a home with a lot of fish aquariums or an indoor swimming pool, then you need HRVs in those settings because you need to get rid of excess humidity. But those are pretty rare. Most residential settings, we're going to want ERVs. Okay, performance matters in general. So how much heat can be recovered? How much humidity can be recovered? It's a good question, and it matters. It's important to be able to quantify the sensible or latent recovery of an HRV or ERV because of several reasons. We want to be able to compare these models if we're going to make a selection of products. We want to be able to compare the products and see which is performing better. So being able to calculate the performance is important. Also, we want to be able to ensure that the supply air, this outdoor air that's coming into the building and being delivered to the living spaces is going to be comfortable. So the performance of the HRV or ERV will impact that comfort. And we said this is a big reason why this matters. Also, we want to be able to calculate the avoided heating and cooling costs. So we know there's going to be an energy penalty to our ventilation. We want to eliminate as much of that energy penalty as we can. Well, how much of it can we eliminate? Calculating the performance will tell us. And then based on what we learn after we calculate the performance, that will help us properly size the heating and cooling equipment. So let's look at an example. Here's just a real simple case study. A 3-bedroom, 1-bath home. Let's say it's 1,500 square feet. Let's say we want an air change rate of 0.3 air changes per hour. That's the ventilation rate, or 60 CFM is the ventilation rate for this house. That's pretty typical, by the way. Let's say the outdoor air is 30 degrees and the indoor air is 70. That gives us a nice round 40 degree delta T. So if we're using a bath fan, let's say we're using a bath fan in 2 different scenarios. Let's say the first scenario is a bath fan being used at 60 CFM in continuous operation, 24/7. It's being used in order to achieve the required continuous ventilation rate of 60 CFM. So that's going to result, if we run our calculation, in 6,200, a little more than 6,200 BTUs per day of thermal energy usage. So that's the energy penalty of using that bath fan. Now, if the bath fan is used more commonly, where it's not even used continuously, it's only used, say, 2 hours a day to provide intermittent ventilation, well, yeah, we'll reduce the thermal energy usage. So we'll reduce the energy penalty of that sort of ventilation to only about a little more than 10,000 BTUs per day. Now, if you remember what our charts look like, though, we'll expect to see much more CO2 and VOC levels inside that space because we're not doing continuous ventilation. Now, in both those cases, we're exhausting stale air out of the house. Well, what temperature is the makeup air? And by makeup air, we mean that air that's leaking in through the cracks of the building assembly. Well, the temperature of that makeup air is the same as the outdoors. It's 30 degrees in this case. So not very comfortable. All right, let's say we use an HRV, and the HRV has 75% efficiency, 75% energy recovery, sensible recovery efficiency. Well, the energy usage of that ventilation solution is almost 16,000 BTUs per day. So it's more than an intermittent bath fan that's only running 2 hours a day. but it's way less. It's, only a quarter of using that bath fan 24/7 to achieve the same ventilation rate. So if we look at the column on the left and the column on the right, we're looking at the same ventilation rate. So our indoor air quality profiles would look the same, but our energy usage and our comfort levels are very different. We're using way less energy with the HRV. And on the right, we see that our makeup air temperature at 75% efficiency is going to be 60 degrees. So that's double the temperature of the incoming air using a bath fan only. So this is a 75% efficient HRV has dramatically improved our energy consumption and dramatically improved the comfort of our makeup air. What if we upped the ante and used a 90% efficient HRV? And these exist. Well, now we've reduced our heating load to even below what the intermittent 2-hour-a-day bath fan required. And we're improving our makeup air temperature even further. Now we're almost at room temperature. Our makeup air temperature is coming in at 66 degrees. Now at 66 degrees, we're near room temperature. And at 60 CFM dispersed throughout the house, that temperature difference between that and the 70, in this case, the 70-degree set point will never be noticed. So we have very high comfort, very low energy consumption. This is a huge win. So we've identified the value of using energy recovery ventilation to help eliminate as much of the energy penalty of ventilation as we can. Now let's look at some highly effective energy recovery ventilation solutions. What do we want to look for when we're doing best practices? First of all, the basic design of the device. We looked at those heat recovery cores or those heat exchanger cores. The shape and design of that core is a big factor. On the top there, you see the cross-flow heat exchanger. Basically, the air streams of those, if you isolated two little air channels, a supply air channel and an exhaust air channel, those two would only cross each other at one point. And so that one point would be the chance that those two air channels have to exchange energy with each other. In a counterflow heat exchanger, this hexagonal shape, the air streams are organized in such a way that they actually go at each other like playing chicken over the distance of the middle of the heat exchanger. So over that, as the air streams take time to pass through that distance, they have more opportunity to exchange energy along the distance of that core. So you get higher opportunity for energy recovery, and you get distinctly higher performance out of this shape. So look for a hexagonal or counterflow heat exchanger. Now, the number of plates stacked together impacts the overall height of the heat exchanger. And the higher the heat exchanger, the bigger the heat exchanger, the more surface area there is. And for the same amount of airflow through a smaller versus a larger heat exchanger, you will get less versus more energy recovery. And so devoting some real estate to the size of the device actually provides better recovery effectiveness. So you want to make some space in the building plan for the HRV or ERV. You'll get better performance. The design of the cabinet and the air tightness, there's a lot of details related to this, but they all impact the performance of the device. So you want to avoid leakage and you want to avoid heat loss, basically. So a well-detailed interior with close fitting tolerances is an important factor in maximizing the performance of the device. You want efficient fans and controls. Look for ECM or electronically commutated motors. These are digitally controlled motors, and they can control the speeds, and there's a lot of benefits to that, as well as the energy consumption of the fans themselves. Where can you find comparisons of these products so that you can compare the values of these different performance metrics? In North America, we have the Home Ventilating Institute. So you go to hvi.org. You can click on the HVI certified products directory, go to section 3, which is HRVs and ERVs, and you can compare and organize the table based on these sorts of values: the sensible recovery efficiency and the power consumed. Now, this won't calculate for you the heating or cooling energy saved, but it will calculate the power consumed by the fans, so you can compare efficiency of the fan motors this way. You can also go to the Passive House Institute and look at their component database. So for units that are Passive House certified, they'll also have comparisons to these metrics. And I believe that Efficiency Vermont has a directory also of certain brands and models that have been evaluated. And so you can look there for things that are appropriate for construction in the state of Vermont. And then besides the unit itself, air distribution methods matter. And so just briefly, we'll talk about this for the last couple minutes here. We think about air distribution. How are we going to get this ventilation air around the building? You might think, well, that doesn't really matter very much. But the fact is it does. You know, something as simple as having a fan and some ducts and a building, you might think you can come up with any combination you want and achieve effectiveness. It really matters. The method of air distribution really matters quite a bit, because the air quality impact room to room is going to make a huge difference. Here's a study that was done by Brian Just of Efficiency Vermont. I believe this was done back in 2015 or 16. So 22 Vermont homes evaluated for a period of 4 nights in the dead of winter sometime. And basically they're measuring CO2 for a period of 4 days. The shaded columns represent the nighttime, and the white columns represent the daytime. And these 22 different homes, CO2 levels hour per hour are charted across this chart left to right. And you can see that CO2 levels are distinctly higher in the bedrooms at night than they are during the day, because that's where the people are. And they're distinctly higher when the doors are closed versus when the doors are open. Now, none of that says very much about the method of air distribution until we separate out the homes. Here we have 3 homes where the air distribution method targeted the bedrooms so that fresh air supply was being delivered directly to the bedrooms. So if you compare 18 other homes where it wasn't, we can see very high CO2 levels in those bedrooms versus the homes where CO2 level was, where fresh air was delivered directly to the bedrooms. Those people, studies have shown that CO2 levels throughout the night will impact how people feel and how they perform the following day. So the people sleeping in these homes with fresh air delivered directly to the bedrooms are waking up more refreshed, generally functioning better day by day because of the air distribution system in their home. It's very common to simply take the supply air from an HRV or ERV and dump it into a forced air system, the return air duct, for instance, and just let it blow around the house based on the furnace or the air handler. This is definitely low on labor and material costs in terms of an installation, but it has very inconsistent impact on indoor air quality. By contrast, a system designed and installed specifically for indoor air quality results is going to be a targeted air distribution system that will extract air from the bathrooms and the kitchens. It will remove that stale air from those polluted areas, recover the energy from that stale air, deliver the energy to cold incoming air, fresh air, and then deliver that fresh air primarily to bedrooms and other living spaces, optimizing the indoor air quality in the living spaces where it matters most. So these are some of the features that you want to look for. Feel free to reach out to me if you have any other questions. If we've got much more expanded presentations on all of this information, and we can share that information with you if you're interested. Reach out, contact me at any time. Thanks for sitting in. If we get ARA credits approved, I'm sure that Bryn will follow up and inform you as to how to get those credits. But that's it for today. If there's any questions, I'm happy to stick around for a few minutes and answer questions.
Thanks so much, Chris. We are at time, so I appreciate if folks need to jump off for other things. As mentioned, we will certainly follow up for AIA credits, assuming we get them approved. You can send your AIA number to us at en@efficiencyvermont.com, and we'll share the list with the attendance list with AIA, so you shouldn't have to do anything. But again, presuming that we do get the thumbs up for credits. Chris, we did have one comment earlier on, and I think you kind of touched on this, but as it relates to CO2, there was mention that it's not correlated with health effects, but I do think you kind of touched on that a little bit in your explanation, but if you just want to revisit it.
Yeah, I'll expand on that. Thanks for the comment. And technically that's, I'll say technically it's incorrect, but it's, so CO2 concentrations in very high levels, like exceeding 5,000 parts per million, definitely that's a health issue. Very few occupied spaces will ever see CO2 concentrations rising to 5,000 parts per million. However, in Brian's study, there was one home where that did occur. OSHA, for instance, sets limits requiring that workers not be occupying spaces that are higher than 5,000 parts per million for more than 8 hours. So that would sort of inform where we want to sleep. However, it's correct that at lower levels, it's not a health issue. The point is not that it creates a health problem, but that it creates, it definitely has been shown by studies to impact cognitive function. So, and this is multiple studies now, not just one. So, so we're not talking about somebody being in a 1,000 to 2,000 parts per million and winding up sick. No, we're talking about people spending time in excessively elevated CO2 levels and then just not being at their best. I think that's the distinction.
Thanks, Chris. We do have another excellent question that's come in. How much increased capacity ERV size should be added to accommodate boost settings for kitchen and bath exhaust when needed?
Yeah, good question. So typically what we do, and I would advise this as a best practice, your boost in kitchens are thorny. Most ERV manufacturers don't want you sucking in grease and things like that if you're making fried chicken on the stovetop. So, but an exhaust in the kitchen somewhere else besides right over the stove is still probably a good idea for the ERV. Boost capacity, usually we like to say, at least 50% more than the nominal ventilation rate. So if you have a typical ventilation rate of say 100 CFM for a house, pick a unit that can give you at least 150 CFM, if not close to 200, so that you can have good boost effectiveness.
Thanks. We have another question here. Is there any new technology being built into whole home ERV, HRV systems to handle high humidity levels, especially when high energy efficient homes are running solely on mini split systems and no central ducts to adapt dehumidifiers?
Yeah, these are all really good questions. That's excellent. What happens in high performance homes is that usually the building envelope is so good that the air conditioning system doesn't need to run very much. And without that call for sensible cooling, the latent cooling potential of the air conditioning system isn't introduced as frequently. What that means is an air conditioning system not only cools a building, but it dries a building. If it doesn't need to run because the building stays cool naturally, then you won't have the dehumidification that comes from AC. So wanting to introduce some whole house dehumidification is going to be necessary. Yes, technology is being developed. This is, I think a lot of manufacturers are probably working on this. I know our company is. Some companies have come out with solutions that are, I'll just say, have some measure of effectiveness, but everybody's, I think, looking to improve that and do better. So yeah, it's definitely something the industry is looking at, and most manufacturers, I think, are. Zehnder is.
Excellent questions. And just to repeat the email address for AIA credit again, it's just EEN, so Efficiency Excellence Network, the acronym for that, at efficiencyvermont, spelled out, .com. That basically just comes to me, and I process that and we'll coordinate everything. So again, my name is Bryn Oakleaf. I am the EEN program manager. If you need to reach me, that is the best way to go about doing that. I think that's it for questions. Chris, thank you for another excellent training today. And thank you to everyone that decided to join us. We are very excited to offer these trainings to you at no cost, and have many more lined up in the coming months. So please come back. And be sure to join us for Better Buildings by Design, April 27th and 28th this year. Very much looking forward to having that in person. So we hope to see you there. Have a great day. Thanks so much.
Thanks, everybody. Thank you, Bryn.
Thank you.